We are now going to move on to a second technique in nonlinear regression, which is called log-log plots. So suppose we wish to predict the weight of an alligator given its length in inches. Okay, length is an easier thing to measure for an alligator than weight is in its natural habitat. So we want to see if we can get the length of the alligator, can we predict its weight? Obviously, as the length of the alligator increases, so should the weight. It increases not linearly, but according to some curve. That curve looks like it could have been exponential, but it turns out that when I plotted this in Excel, that it told me that a power function is actually the best fit. So we want to explore why that is the case. Okay, so what type of relationship exists between W and the length L? Okay, so we believe that there's a power function relationship. So W equals CL to the K. And what is the significance of that power relationship? It's that W is then proportional to L to the K. Okay, when you see a constant, that one quantity is a constant multiple of another, then the relationship between those two quantities is a proportional relationship. So the way that we're going to investigate this, like I said before, is via what's called a log-log plot. That is a plot of the natural log of W versus the natural log of L. So what I've done is I've made a list of the data points where I've done the natural log of the length and the natural log of the weight. Okay, and then when I plotted it, notice that when I'm looking at this log-log plot, that again, it appears that a line is the best fit, that there's a linear relationship between the natural log of those two quantities. So the resulting plot is linear. Now, why would that be the case? Well, the natural log of W is going to be the natural log of CL to the K. That is the natural log of C plus the natural log of L to the K using our log rules. But also we can write that as the natural log of C plus K times the natural log of L. Now, that actually shows that there's a linear relationship. So natural log of W is equal to a constant, maybe we'll call natural log of C beta 0, plus another constant, we'll call that K, well maybe they'll call that beta sub 1. And then we can think about natural log of L as being X. Okay, if we think about natural log of W as being Y, then when we have a relationship, Y equals beta 0 plus beta 1 times X. Okay, but in this case, Y and X are the natural logs of our two variables. Okay, and that explains why when we did the log-log plot, it looked like the data was a line. So now our technique is going to be the same as it was with the semi-log plot. We're going to look at the log of the input and the output variables. We're going to plot that. And then we're going to try to find the regression for that linear relationship. Notice that the regression given by Excel is there. And notice that the R-squared value is 0.9808. So again, the coefficient of determination is very close to 1, which tells us there is a linear relationship between the log of W and the log of L. Okay? So once I've found that linear relationship, how can I get that back to being a power fit? Okay, how do I get the curvy function for alligator size that I have up here? Okay, so given that linear fit, okay, our linear fit's going to be of the form natural log of W. It's going to equal beta 0 hat plus beta 1 hat times the natural log of L. And then I'm going to do the same thing I did before. I'm going to do the e to both sides. E to the natural log of W is going to equal e to the beta 0 plus beta 1 natural log of L. I can write that as e to the beta 0 times e to the, and then I'm going to write this as natural log of L to the beta 1 power. So I'm going to kind of reverse that property of natural logs and take the constant out front and make it the power of L. Here, actually, let me put the parentheses right there so you can see that. Okay, so W in this case then is just a constant times L to the beta 1 hat, and that constant is going to be e to the beta 0 hat. Okay, so that gives us the technique for once we have the regression line for the log-log plot, then we can turn it back into the power fit. So let's do this. Let's actually work through this whole example. This is really good review, okay, of all the things that we've done so far. So for the sample of 15 alligators, we let x be natural log L and y be natural log W, and then I found x bar and y bar and s sub xx, s sub yy, and s sub xy. So beta 1 hat, our approximate slope is s sub xy over s sub xx. That is 2.933 over 0.8548, gives us a total of 3.4312. And then I want to find my intercept, beta 0 hat. That, of course, is y bar minus beta 1 hat x bar. So we're going to take 4.418, subtract the slope, 3.4312, times x bar, which is 3.758. And we get a negative 8.476. So our regression line is that the natural log of W equals negative 8.476 plus 3.4312 times the natural log of L. And I really like to write this with the natural logs because then it gives me a sense of how would I solve for W. I would just do e to the W. Okay, so the book is actually going to write this probably as y here and x here, but I like using the natural log W and the natural log L. In this case, it tells me, again, how to solve for W. Okay, so what is W? W, as we saw before, I'll kind of sneak back up here so that we can see, is the constant, which is e to the beta 0 hat times L to the beta 1 hat. So in this case, it is e to the negative 8.476 times L to the 3.4312. And so I'm going to actually write this as W equals 0.0002. That's what e to the minus 8.476 is. L to the 3.4312. And that gives me the relationship between the weight and the length. That says that weight is actually proportional to L to the 3.4312 power. I want you to notice that it's kind of close to L cubed, right? And length cubed, that should be something like volume. Okay, so what we're saying is that weight is going to be somehow proportional to a volume. Of course, it's not exactly 3, okay, because, right, our alligators are not spherical, okay, or they're not a cube or something like that, okay, but the relationship, you can kind of see that weight is proportional to volume. Now, I want to show you how you can use this information, okay, to say predict the weight of an alligator that is 54 inches long. So I want to do that. Okay, so let's find a 90% prediction interval for the weight of an alligator that's 54 inches long. Okay, so we want to find a 90% prediction interval. First, I'm going to do that for x star, which is going to be the natural log of our length, right? Because x, as we saw above, we said was the natural log of length. Okay, so in this instance, we're going to let x star be the natural log of 54 inches. That's going to give us 3.989. Now, something else that I'm going to need for this prediction interval is going to be the sample standard deviation. We'll remember that that's the square root of the sum of the squares of the error over n minus 2. I didn't give you the sum of the squares of the error. I gave you other information. So we're going to need that the sum of the squares of the error is SYY minus beta 1 hat S sub X XY. Again, we're going to divide by n minus 2 here. Okay, so that's going to be the square root. S sub yy, when we were looking above, was 10.26. We're going to subtract the slope, 3.4312 times 2.933. Okay, we're going to divide that by 15 minus 2. And if we work that out, we actually get the 0.123, and that is our sample standard deviation. Okay, so our prediction interval is going to look like beta 0 hat plus beta 1 hat times x star, and that's going to be plus or minus our t value for 0.05, okay, and n minus 2 degrees of freedom times s times the square root of 1 plus 1 over n plus x star minus x bar squared over s sub x x. Okay, so we just need to compute all of these values. Beta 0 plus beta 1 hat x star. Okay, so beta 0 is negative 8.476. So we have negative 8.476 plus, we're going to do 3.4312 times x star, which is 3.989. And then I need to add my t statistic. So I'm going to have to look at my t distribution chart for degrees of freedom of 15 minus 2, which is 13. So I'm going to look at my t statistic, or t distribution chart. Okay, I'm looking at the 0.05 column here. Okay, degrees of freedom of 13 gives me 1.771. So now I'm going to go back here so that I'm going to get 1.771 times 0.123. That's what S is. And then I'm going to take the square root of 1 plus 1 over n, which is 15, times 3.989 minus 3.758 squared. And then I'm going to divide that by S sub xx, which was 0.8548. Okay, that long computation is going to give me, let's see, 5.211 for that first part, okay, plus or minus, and then the second part ends up being 0.2312. So what I get is a confidence interval that looks like 4.979 to 5.442. And I misspoke there, not a confidence interval, a prediction interval. Okay, so we can say that if an alligator is 54 inches long, that the natural log of the weight appears in this interval. Okay, so with probability 0.9. So this is for the natural log, the natural log of the length. Okay, what about the 90% prediction interval? Okay, for instead of X star, we want to do the 90% prediction interval for L star. Okay, what is that going to be? Okay, let me just fix this up. Okay, so I should say really that this confidence interval isn't for L star. It's for W of L star. That's a better way to put that. Okay. So what is the 90% prediction interval if I'm given a certain length? Okay. Again, just making a little fix here. It's not W, it's the natural log of W. That's better. Okay. So now I want to find the 90% prediction interval if I'm given L star, okay, in this case is 54 inches long. Okay, so how do I figure that out? Well, I could just solve for W by doing E, like I just did there. So I could do E to this and E to that, and that will give me my prediction interval. Okay, and so that's exactly what I'm going to do. Okay, so I'm going to do E to the 4.979 to E to the 5.442, okay, and that will now work, okay, for E to the natural log W, which of course we know is W. So our prediction interval, when we work this out, is 145.975 pounds to 230.856 pounds. Okay, and so that is my 90% prediction interval for the weight, which depends on L star. And what I want you to notice is it's much wider than the first interval that we got. Okay, so the first interval that we got was for the natural log, and so it only went from 4.9 to 5.4, right? But now when I look at the exponential, right, now we're going from 145 pounds to over 230 pounds. Okay, and so this method is just not going to be as accurate when we're dealing with nonlinear regression like it was, say, when we were dealing with linear regression. Our confidence intervals and our prediction intervals are going to be much wider. This is why it's important, and you may not have noticed, but I carried a lot of digits in these calculations, more digits than even I showed you. And I carried all those digits because I knew I was going to do an exponential to those numbers that I found for my prediction interval, and I knew that the error was just going to get bigger and bigger if I didn't carry all the digits. And so that's why it's really important with these computations that you continue to carry all of the digits. So hopefully that gives you a sense of how you can use these nonlinear regressions to make predictions or even find other intervals like confidence intervals.